Okay, here we have the third watershed problem. It involves a much smaller watershed than the last one with an area of only 2 square kilometers. And we're given once again, that the change in water stored is 0. I guess I can use a different color there, right? So that once again, there is no change in storage. We're given precipitation rate, we're given evapotranspiration rate, and we're given stream flow. And we're asked to calculate the average annual groundwater outflow. So this is a little bit tricky in that which was not mentioned here, but is an integral part of this problem, is runoff. So once again, let me write the general storage equation for a watershed that we often use. It's the change in storage with time is equal to precipitation in minus evapotranspiration out minus runoff. And remember, runoff, let's put that in a different color here just to be clear, and runoff is the sum of stream flow and groundwater out. So in this problem, our strategy, notice that we're given, let's just be clear again, we're given storage, that's going to be 0. We're given precipitation, we're given evapotranspiration. So from that, we should be able to calculate runoff. And then once we know runoff, something we will know, and we're already given stream flow, we should be able to calculate our final goal here, groundwater out. So our task is going to be to first calculate runoff, and then knowing runoff, calculate the outflows of groundwater. So let's just write down what we know here. So once again, we have that nicely, that the the storage is equal to 0. And we're going to have to convert precipitation and evapotranspiration into a volume per time unit. So let's write this storage equation as 0 equals the volume per time from precipitation, mu sub p, minus the volume per time lost by evapotranspiration, minus the volume per time lost as runoff. And we're going to solve this as the volume, we're solving for runoff, right? The volume per time of runoff is going to be equal to the difference between the volume per time of precipitation and the volume per time of evapotranspiration. And just like in problem 2, we're going to have to convert these precipitate. We're going to have to actually convert these precipitation and evapotranspiration rates into a volume per time by multiplying them in appropriate units times the area of the watershed. So let's first compute. We're going to do everything in terms of meters cubed per year. That seems to make more sense. In fact, I'm told to do that. So let's first convert the area of the watershed into meters squared. There you have it. The area of 2 square kilometers is equivalent to 2 million meters squared. Now, knowing this area, we can calculate the volume per time of both precipitation and evapotranspiration by multiplying the rate in meters per year times the area in meters squared. So for example, for precipitation, we will write that the volume per time of precipitation turns out to be a little more than 1.25 million cubic meters per year, and for evapotranspiration we write the following: that the evapotranspiration volume per time subtracted from the watershed is 860,000 cubic meters per year. And we're almost done. We just have to take the difference between those two. We're going to subtract. Actually, I can just draw it like this, right? I'm just going to subtract this. I'm just going to subtract 860,000 from 1,270,000. I'm going to subtract that, and that will be my volume of runoff lost from the watershed, and that will turn out to be 410,000 cubic meters per year. So this is the first part of the problem. And remember that runoff is the sum of stream flow and groundwater flow. And so I guess I can write over here that since runoff equals the sum of, and once again, all of these are in volume per time, the mu variable here, the sum of stream flow and groundwater flow out, right? I can write that the groundwater flow out, which is really our final destination, that's what we really want, is equal to that runoff number I just calculated minus the volume per time lost from the watershed due to stream flow. So this is going to require one little additional calculation because of course the stream flow wasn't given in volume per time. It was given in volume per time, but it was given in the sort of instantaneous unit of cubic meters per second, and I'm going to have to change that to cubic meters per year. So let's go do that first. This here is the average stream flow in cubic meters per second, and to convert that into cubic meters per year, I'm just going to multiply by a whole bunch of time conversion factors, with a final answer of 380,000, about 380,000 cubic meters per year. I'm just going to call attention to the fact that once again we can notice that all these units are going to cancel for us. We set it up properly, leaving us with the final units of cubic meters per year, which is what we wanted. So 380,000 cubic meters per year. That is stream flow, and so we will then get the runoff. Again, just slide down here. We'll get the runoff by the difference between those two numbers. So this equation here, right, will give us the volume per time of runoff. And so what we're going to do is we're going to subtract this number, the stream flow, from this number, the runoff, and that will give us the groundwater flow lost from the watershed. So let's just do that and we're done. Heck, we can almost do that in our head. So we get 410,000 minus essentially 380,000, and that leaves a difference of 30,000 cubic meters a year, which is the groundwater flow lost from the watershed per year. And we're done.